Hello again. So from now on, we'll be focusing on the transformation of stresses in two dimensions. As I was mentioning in the previous part of my lecture, uh, if we have a general three-dimensional body like this, a general two-dimensional body like this, we are no longer considering three-dimensional bodies. So this is very much 2D. Uh, and we focus our attention at a particular point Q inside it. Now if we were to choose a coordinate axis in this fashion, then to investigate the state of stress at the point Q, so this is our point Q. So to investigate the state of stress, the two-dimensional state of stress at the point Q, referred to this choice of our coordinate system, we would take a little element in this fashion. We take a little element like this, centered around Q. On the other hand, if we were interested in considering another coordinate system, so for example, we just copy our two-dimensional body here. So that's nicely done. And we consider the same point Q here. But this time we want to consider axes which are not the x and y axis, rather these are our new axis x dash and y dash, which is somewhat tilted. Please note that we are considering the same two-dimensional body. We are again considering the same point Q. It is only the choice of the coordinate axis which has changed now. Corresponding to this new choice of coordinate axis x dash and y dash, we choose a little element centered around Q again, but which is also rotated relative to the previous element, the blue square element that we had considered here on the left hand side. So the physical situation, despite remaining the same in both the cases, it is the choice of the coordinate axis which has changed, and because of this, the state of stress which will be describing, or the stress components which will be describing the state of stress at the point Q in the two cases will be different. So what I mean to say is that on the left hand side we are going to have sigma xx, sigma yy, and tau xy, while on the right hand side we are going to have sigma x dash, sigma y dash, and tau x dash, y dash. The question which we want to answer as the primary topic of discussion of this chapter is that what is the mathematical relationship between sigma x dash and sigma xx, sigma yy, tau xy? What is the relationship between tau x dash, tau tau x dash y dash, and sigma xx, sigma yy, and tau xy. How can we find that out? So towards that end, what we are going to do is consider a very special kind of element which will uh, help us through a force balance to find out this relationship. So let's do that. We'll consider a side like this and a side like this, but we are not going to complete the square. Rather, we are going to understand that this vertical edge represents an edge which is parallel to the y-axis in the left hand side of the diagram, and this horizontal edge here, it represents an edge which is parallel to the x-axis on the left hand side of the diagram. To complete this picture, we are going to draw a side which is perpendicular to the x dash axis, or which is parallel to the y dash axis, referring to the right hand side of the above diagram. So we have our coordinate axis. If we were to superimpose the coordinate axis from the previous diagrams here, it would look somewhat like this. We will have our x dash here, we would have our y dash here, and our x would be present here and our y would be present here. The information which we absolutely know is the angle between x dash and x, or equivalently the angle between y dash and y. So we know this angle. Let's call that as theta. Now what we want to do is carry out a force balance along the x dash direction first, and then a force balance in the y dash direction. But before we do that, we identify the three vertices as L, M, N. Now, what we want to do first of all is to note that on the face LM, the stress components which will appear are sigma xx and tau xy. So we write them down. Similarly, on the edge MN, the stress components which are going to appear are sigma yy and tau xy, while on the edge Ln, the stress components that are going to appear are sigma x dash and tau x dash y dash. All right. Uh, for the purpose of the force balance, it will be important to take various components. Uh, Not only do we have to take the force components associated with the various stress components, but we'll also have to take the components of the areas which represent the areas of these along these edges. So, for example, if we denote the area uh, along the face LN, so you understand that in a real three-dimensional situation, this would be a face ln going into the plane of the paper, maybe of unit width. So we say that ln edge, that is the projection of an actual area which is going into the plane of the paper, and let us say that that area uh, is depicted by the capital letter A. So the area of this edge ln is A. Now if this angle is theta, so if this angle is theta, then we know that this angle will also be theta, which means this angle would be theta, and this angle would be 90° minus theta. So we are now in a position to go ahead and do the force balance along the x direction. So sigma f x dash is equal to 0. So what that will give us, and remember that we have to keep track of the components of the forces which are associated with the various stress components properly, as well as the directions. So we have to take the component of the force which is associated with this stress component sigma xx along the x direction. Similarly for this tau xy, for the sigma yy and the tau xy. So first of all, considering the edge LM, we write sigma xx first of all. The area of the face LM would be a cos theta, because we see here that this angle is theta, this is A, so LM would be A cos theta. So we can write it down here. So ln has area A, this is the area, Lm is A cos theta, and Mn is A sin theta. So what we are writing here is sigma xx Lm, so that is basically A cos theta. Now this is the force which is acting along the negative x direction. Now we want this force, we want the component of this force along the x dash direction, so or along the x dash direction. So what we want to do is take the component of this, noting that this particular force, so if you are looking at this, this is making an angle theta. So you understand that this is the line which is parallel to the x dash direction. So we have to take a cos theta here. And there's a minus here. Sorry. There's a minus here because it is along the negative x dash direction. Next, again considering the phase LM, we have the contribution from tau xy. So without writing minus or plus, first write down the contribution from tau xy, the force due to tau xy, which will be also along, which will be multiplied with a cos theta because it is along LM. And we have to take the component of this force which is acting along the negative y direction, because you see that this is the force will be along this direction. So this is the negative y direction, and we have to take the component of this along this line again, and this angle is 90 degree minus theta. So this is a sine theta, and this is again in the negative x direction, so we have a minus here. Next, we are going to consider the edge MN, and the first force that we are going to consider on the edge MN is the one associated with sigma yy. So the force associated with this thing. So again, before without writing any minus or plus, we considered the force, the sigma yy, multiplied with Mn. Mn has the area a sine theta, as you can see here. Now this force is acting along the minus y direction, and we have to take the component of it parallel to x dash. Now this angle is again 90 degree minus theta, so this is cos of 90 degree minus theta, so that is a sine theta, and because it is acting along the negative x direction, there should be a minus here. And finally, we are going to take the force contribution due to this tau xy. So tau xy, a sine theta. This a sine theta comes because we are considering the edge Mn, and then we have to take the component of this force along the x direction, and you note that the angle that this force makes with the x direction is nothing but theta, so that's a cos theta here, but this is along the negative x direction, so we need a minus sign here. And finally, we should not forget the edge Ln, on which the force which is acting along the x dash direction is simply sigma x dash multiplied with a, and we don't have to take any component because this is entirely along the x dash direction, and this is very much with a positive sign. This is equal to 0. So overall what we have, and you can see that from all the terms the area cancels, so what we'll have eventually is sigma x dash is equal to sigma xx cos square theta plus sigma yy sine square theta plus 2 tau xy sine theta cos theta. That's it. So in the next part of the lecture, we are going to address the summation of the force along the y dash direction.